Margulis lemma, וגם באיזה רץ. is as you already realized, it's a central center important in all this investigation. So we will discuss it several times. So we will discuss various versions of it, which will be according to what we will need to. But if you write in this morning, I wrote in Google, and you get to Wikipedia about Margulis lemma, you will get the following version, which is what I will prove today. So, in fact, let me even be okay. Suppose so. Let so in what do I want? So what I say it applies in non-positive curvature. In the Lie group case, I will have even stronger information. In the case when consider arithmetic groups, I will have even stronger information. Okay. So fix for a given D, for a given n, this is the dimension. There are two constants, epsilon and m. Such that if X is a Hadamard manifold, let's take this. This is the first time we see the Margulis lemma, so let's stay with the symmetric space. So if X is a symmetric space, of dimension n, and gamma in the isometric group of X. So the isometric group is now a Lie group. Symmetric space, the isometric group is a Lie group. In fact, for any Riemannian manifold, the isometric group is a Lie group. Usually it's a discrete group. Usually there are not so many isometries. But now the isometric group is a Lie group that acts transitively, and X is G mod K, and actually this Lie group is even linear, so it's a semi-simple Lie group. So a joint semi-simple Lie group. The connected component is linear, so everything will be simpler to prove. Although what I write will hold in a general, more general. Gamma is a discrete group. Such that there is some X inside X for which gamma is generated, or maybe not, maybe like in a discrete group. Then for any X in X, the group gamma X, Thurston called this group generated by small elements in X. So this is the group of all elements generated by the elements in gamma, such that the displacement of x, I remind you that the displacement is the distance between gamma x to x. If you want, in the quotient manifold, it corresponds to the length of the loop, the closed loop that takes you from this point to this point, so closed loop around x. So the displacement is less than epsilon. I look at all elements that displace x by less than epsilon, and I look at the group that they generate. So this group is virtually important. It's a simple, it couldn't be too complicated. So this group has an important subgroup of index of most n. So this is the Margulis lemma. It tells us that groups generated by small elements are virtually important. So I will prove this and then deduce from this the fixed in decomposition. That will be what we will do in the rest of the time today. Maybe a bit about history. So I didn't prepare for that, but the idea behind this lemma, or version of this lemma, appeared many times in the history, probably first in Jordan's theorem. Jordan proved that in GLNC, if you have a finite subgroup, then it has a subgroup of index M, which is abelian. It's a classical statement about finite linear groups, and the proof is basically, it's a version of Margulis lemma. Then Zassenhaus proved another version, and then Kashdan Margulis proved another version. Margulis at some point proved something which was in the most general maybe case, and I think the name, it's called Margulis lemma because, because of either Gromov or Thurston who named it after him, but so the idea appeared several times. Also, there are variants of it. We will see, in fact, I don't want to spend that time on it today because for the application for today we don't need it, but we will see that the subgroup of index M, it's not just nilpotent, but it's contained in a connected nilpotent Lie group. We can find a connected nilpotent Lie group inside this group, which will contain this subgroup of index M. And this is much stronger information because we understand a lot about connected nilpotent group. We understand more about them. For instance, in some cases it must be abelian. Connected nilpotent group must be abelian in some cases. In the rank 1 case, for instance. No. Okay, in some cases you know it's abelian. You know with the rank, the nilpotent is C rank. You know more about it. So this another version that we will need later. So I will discuss the. Okay. So the idea is this is a consequence of the following lemma of Zassenhaus. Let's discuss the proof. So let's assume that that G, suppose G, the isometric group of X, is a subgroup of a general linear group over R. And this assumption will simplify something, but it's not a real something. It's not a real issue because first, it's true. because when you consider symmetric space, the isometry group is a semi-simple adjoint group, and it's the adjoint representation give you an embedding of it in GLK, where K is the dimension of the Lie algebra. So you can assume. But what I say next will apply to any Lie group, and any Lie group there is this theorem of Edo Iwasawa that says that any Lie algebra is linear, and when you interpret it to Lie group, it says that any Lie group is locally isomorphic to a linear group, and all what I'm going to say preserved under local isomorphism. So I'm not restricting anything. I mean, you can prove the general case, a more general case, by assuming that. So then, thus in our spoon, thus in our show the following. There is an identity neighborhood omega such that omega to the n, I will in a minute define it, converge to 1. So I need to define what is omega to the n and what is converging to 1. So if definition, if H is a group, we define and S is a subset of H. Sn defined to be the sets of all commutators between S and Sn minus 1. Well, the commutators of two sets is by definition the sets of all commutators A and B, A in A and B in B, and just to make it clear, because we speak about Lie groups and not Lie algebra, this is A, B, A inverse, B inverse. So this is the set of all commutators. And so there is a small identity neighborhood such that the commutators goes to 1, and goes to 1 means i.e. Eventually enter any ID neighborhood. So you should imagine this group G, it's a big group, there is identity neighborhood, and then there is omega, and inside omega you have okay, let's say that omega, let's say that S0 is S, so then you have omega 1, and then omega 2, and then it becomes smaller and smaller. Doing commutator. When basically this is the intuition is very clear. I mean, a Lie algebra is commutative. Lie algebra is so what's the intuition? The intuition is that the commutator of things which are close to the identity should be much closer. But okay, instead of intuition, let's since we discussed symmetric groups, so the proof is very simple. So
you don't need omega to be open.
So
You don't need omega to be open.
So it's a neighborhood. So it's contained a neighborhood of identity, and it's basically, I will say what it is. So of course, if a subset of a set with this property will also have this property. so you can take it to be open. And I will tell you exactly what it is. So in fact, it's enough to prove, since G is inside GLK, it's enough to show that there is such omega for GLK. And I tell you what is omega. All in a sense, in a minute I will tell you. So first some calculation. If A is the identity plus A, so now it's matrices, so I can write it like that. And B is the identity plus B. And let's say that the norm of A and the norm of B are small, smaller than, say, delta. And let's now see so they are close, they are delta close to 1. Let's see what's happened when we do commutator. So A, B, A inverse B minus 1. Well, let's say that one of them is less than delta 1, and one of the other is less than delta 2. Let's see what happens. Both of them are close, because one of them will be closer than the other later. And then, so this I can write the same as, if you think about it, AB minus, no, this you can write as AB minus BA times A inverse B inverse. And this is the same as AB minus BA. A inverse B inverse.
Is there a missing inverse in the one line up? The first term.
What? So. Thanks. And this you can write it in this way. And now, if delta 1 and delta 2 are sufficiently close, sufficiently small, if a matrix is close to the identity, then its inverse is also close to the identity. So I can assume that, okay, this is less than the norm of twice the norm of A, the norm of B, times the norm of A inverse times the norm of B inverse, because the norm is submultiplicative. You know this property from norm of matrices. And I can assume that this is less than 2 and this is less than 2. Because if the norm of 1 is 1, and if you're close to 1, then your inverse is also close to 1, and the norm is, taking inverse is continuous. And so we have this. So this is smaller than, if you want, 8, delta 1, delta 2. So you see, if both of them were delta close, then now you are delta square close. You are much closer. And this basically shows that you can take a Zassenhaus neighborhood, so corollary of this heuristic for GLN, GLK, and you can take omega, a Zassenhaus neighborhood, to be all matrices such that the norm of A minus 1 is less than 1 over 8 or 1 over 10, at least. Let's say 1 over 10. So it's
if you want A and B inverse to be less than 2, then I think you need it depends on the
yeah. Right. You need okay. So a computable constant. There is a computable constant delta that depends on the dimension. That thank you. So so this is the first observation, and then the second observation. So now we discussed we discuss a discrete group. So this neighborhood is the Zassenhaus neighborhood. So omega is called the Zassenhaus neighborhood. The Zassenhaus. So that's a nice neighborhood. Every Lie group, every connected Lie group has that's a nice neighborhood. It's a neighborhood. Sometimes you also require that you require more, but you sometimes require that the logarithm will be well defined there. So you could take it even smaller, but it's a neighborhood with this property. And then,
can you explain again the corollary?
Why this is a neighborhood? That's enough.
Yeah. And
suppose this delta 1 is less than 1 over 10 and delta 2 is less than 1 over 10. Then after I do the commutator, first both of them was 1 over 10 close to that. And then after the commutator, they are 1 over, or let's say 1 over 100. So after I do the commutator, there is 1 over 10,000 times 8, so there are at least 1 over 1,000 close. So after the commutator, they will be much closer.
Is there a reason we looked at delta 1 and delta 2 in the
Yeah,
reasoning?
because when I do this, if you remember omega n, I take, it's the commutator of omega n minus 1, not with itself, but with omega. So I take 1 from here and 1 from here.
Why not take it with itself?
Then it only
Because I want, you will see now, I want to get nilpotency and not just solvability. Nilpotency is strong in both things. So that's why, yeah. So here is a exercise. I will solve it for you, but it's a, let's say a lemma. It's a nice lemma. So let gamma be a group generated by a set S, and suppose for some n, S to the n is trivial. Then gamma is nilpotent of rank n. Okay? And what is the proof? Proof. So I write the first line of the proof. S to the n minus 1 commute with everything. Because we do commutator with S, they commute with the generator, so they commute with everything. So the group they generate is central. And if I look at, so let's call it C. And if I look at gamma mod C, is generated by S mod C. Again, how do I write it? Let's write this, where S is all the element of SC, S in S, and S to the power n minus 1 is trivial. So it satisfies the same property. The quotient satisfies exactly the same, but with smaller n. So by induction, if a group, that's one of the characterization of nilpotent group. A group is nilpotent if and only if it has a center, and modulo the center is nilpotent. So by induction, you see that gamma is nilpotent. Okay, is this clear enough? So such a group is important. So now you can prove the following proposition of Zassenhaus. And again, there is a stronger version. If you look at Google or in Ragonathan's book for Zassenhaus theorem, you will find a stronger version. But for now, let me just prove Zassenhaus theorem but this is a single version. So a Lie group, any Lie group, a connected Lie group. G has a neighborhood ID, neighborhood omega, such that if gamma is discrete, then gamma intersection with omega is important. And what is the stronger version? The stronger version, it's not just that this is important, but this is contained in a connected important group. And to prove the stronger, you need also to assume that omega is sufficiently small so that the logarithm is well defined. And you do basically what we did here, but with the logarithm in the Lie algebra level, and then you find an important Lie algebra and take its exponent and blah, blah, blah. So it's very similar. It's just more technically more complicated. And for the first application, I will not need it. I will only need this. So it's much simpler. So, and why is that? By the lemma proof. Take omega as before. So omega to the n goes to the identity. It never gets there, but it's going. And this implies that write S equals omega intersection with gamma. Then S to the n goes to 1. But this is a discrete, this is a finite set. How can it converge to 1? It must be trivial. So this is inside a discrete group, because gamma is discrete. So if you converge to the something in discrete group, you will get there actually after a finite step. So this implies that S to some fix is 1. Hence, by the lemma, the previous lemma, gamma is negative. Okay?
Gamma intersection.
No, gamma is generated by the intersection. Gamma is generated, this is what I denoted by S. Gamma is generated by S. Ah, no. Yeah. Thank you. S. Yeah, thank you. I confuse myself because sometimes you say, suppose gamma is discrete and generated by its intersection, but okay, that's better explanation. So, so this is the Zassenhaus theorem, and now we deduce the Margulis lemma. So let's prove the Margulis lemma. And in the real theorem of Zassenhaus, again, it's not just that that this group is important, but it's contained in a connected important group. And when we will need it for application, we will modify the Margulis lemma. So the proof of the Margulis lemma will be just the same. So how do we do that? So recall that X is a symmetric space, is G mod K, where K is maximal compact. And recall that G acts on X transitively and properly. if you want me to remind one of the notions, then say. And now I want to tell you. Now, the thing is that.
What do you mean by properly?
Properly, I mean that. Properly means that for any. Properly means that for any C in X compact, all G in G such that GC intersect C
It's compact.
is compact. Basically, it follows immediately from the fact that it acts by isometries and the stabilizer are compact. So, so it acts properly. And now I want to prove Margulis lemma. So let gamma be a discrete subset. So to say that gamma acts, yeah, let gamma be a discrete subset. But I will find some epsilon and m which are independent, which will work for n with gamma. Okay.
So the definition, what's the group? So it's all G and G and such that?
This I want to remind what is what proper means. Proper means, yeah, proper action means that all the G that translate this compact set to something which is not disjoint is compact. And now, okay, thinking it seems enough. So I will find epsilon and m, and let's do it. So let's define B1 or fix x0, fix x0 inside x. Let's say that it's a fixed point of k. So k x0 equals x0. Any point in G mod k corresponds to the stabilizer of it is a conjugate of k. So I fix it, the action is transitive, so the constant that will appear now will be independent of x0. I could take any other point. And now consider B1 to be the set of all G such that the distance from G x0 to x0 is less than or equal to 1. It's a compact set. So this is compact. So B1 is compact, so B1 is compact. Okay. Now, I'm going to proceed. So let U inside G be a symmetric. Symmetric means that it's equal to its inverse, ID neighborhood. Such that U square is inside omega, is inside the Zassenas network. Okay. Now if gamma is discrete, So so let M be the Haar measure of B1 divided by the Haar measure of U. And let's take a plus one. Probably this is enough. So this is some integer. So this is a compact set, this is an open set, this is something. And let epsilon be 1 over n. So this will be the two constants in the Margulis lemma.
And why do they only depend on?
What?
You say they only depend on the dimension?
Now I fix G. So once you fix G,
Okay.
they don't depend on anything. If the dimension is what you care, there are only finitely many symmetric spaces of a given dimension. So there are finitely many G. But so once you fix G, the constants are constants that's associated with G. And now I want to show, okay, so let gamma be a discrete group such that gamma is generated by all gamma such that the gamma of x naught is less than epsilon. And so I want to show that gamma is a subgroup of index M which is nilpotent. Now, and I claim that this is independent of x naught because the action is transitive, so you can conjugate. So this will prove. If approved, we need to show. It's enough to show that gamma has a subgroup. Let's call it N, which is an important subgroup. N such that gamma mod N is less than N. And in the Margulis lemma, there was general X and now it's X naught, but since the action is transitive. Okay, I will tell you what is N.
Yeah, can you, since the action is transitive, but still the displacement of two different points can be different, right? So even
Sorry?
after, could it?
Yeah, but here I prove here a priori the constant depends on x naught, right? But they don't, because if you take another x naught, take the associated b1 for the other x naught, it will have exactly the same Haar measure.
Okay.
And take the corresponding conjugate of u, it will have, yeah, maybe somewhere hidden here the fact that G is only modular, but let's leave it as an exercise to verify why.
You can just conjugate gamma, right?
Yeah, okay, you can conjugate gamma. Right. But okay, yeah. I mean, you solve it one way or the one way or another.
But suppose it satisfies it for some x1, then you take an element in G, and which conjugating gamma will make it satisfied for x naught.
Okay.
This conjugation is an isomorphism, so if this new gamma, the conjugation of gamma, has an n such that the quotient is least.
Okay, I don't.
There is an issue here to check. I will leave it as an exercise. What?
Maybe you just make unilateral.
conjugate.
Yeah, I don't, let's not discuss it now because I want to finish on time, and yeah, let's leave it. There is an issue why this x is why it's not really depend on x. I mean, there are several ways to see it, but somehow okay. I don't want to focus on that because I managed to confirm myself. I want to see if I can finish the proof. So I tell you what is n. N will be the group generated by u square. The intersection of gamma with u square. We said u square is inside omega, so this is an important group. And now I need to what we need in order to finish, we need to show that we need to show that the index of gamma of n is less than n. And this will furnish the proof. Okay. So let me just tell you something. So we prove that given x naught, there is m and epsilon. But m, that epsilon is 1 over m, and m is given by this. And if you take another x naught, you will see they have the same volume. The action is by zone. So the space is it cannot a statement like that cannot depend on x because the space is homogeneous. All x are the same. But okay, but I don't want to spend time on that. I want to show that this index is bigger than, is smaller or equal to m. Suppose in way of contradiction, suppose the contrary. I.e. that gamma mod n is at least n plus 1. And look at the Schreier graph. Consider the Schreier graph. How many mistakes there?
I think you need a C before the H and then it's okay.
E with an E instead of a.
S C H
Or
E.
E I.
I
Ah.
Okay, Schreier graph.
It's
E I no.
Let's call it
No, it's
Schreier graph of gamma mod n with respect to the generating set S, where the generating set S is all gamma such that the gamma is less than epsilon.
Sorry, can we just say we have gamma twice? So the gamma is gamma x naught, and the big gamma is a discrete group we started.
yeah.
Just
What?
like, it seems like you defined gamma with gamma or gamma,
I said let gamma be a discrete group
Right.
such that
but then you define gamma with gamma. So you're defining gamma x naught.
yes, let it be a discrete group which is generated.
by one
Uh,
of its elements.
Let gamma be a discrete group and suppose it is generated by this. Okay.
Okay.
Yeah. I mean. Okay. So this is a set of generators. Okay. Now there is a nice observation. So this is a connected graph. Schreier graph is a connected graph because it's with respect to generating set. If a graph has more than m vertices, suppose a graph has at least m plus 1 vertices, then the m ball in the graph has more than m plus 1 vertices. The mth ball in the graph has at least m plus 1 vertices. Right? The graph, if it has more than m plus 1 vertices, because the zero ball has one vertex. The next ball has at least two vertices. The next, if it's stabilized at some radius, then it's the whole graph. Otherwise, it has, so with the m ball, so this is, it's obvious, but you need to say it. So the m ball, so this implies there are, let's say, gamma 1 up to gamma m plus 1, this different disjoint element inside S to the power m, such that gamma I n is not gamma j n for all I different than j. This is what it says. Okay. And this is a contradiction. Why? Recall that maybe denote the generator set by S1 up to Sk. So so the displacement of Si of x naught is less than epsilon, which is 1 over m. And this implies that the displacement of gamma I of x naught, it's not the same I. The displacement of gamma I is less than m times epsilon, which is less than 1. Right? Okay, you will. Because this actually also need a justification. All of them display as displacement less than 1 over m, so the product of m of those is displacement at most 1. This needs a justification, but I will do it in a minute. But this implies that that's gamma 1 up to gamma m plus 1 are all inside B1. You remember? B1 was the set of all G such that the displacement of x naught is less than 1. However, this implies that gamma I u intersect gamma j u trivially, because u square, u is symmetric, u equals u inverse, and u square is right. What you, if you remember, how do we define n? N was gamma, the group generated by gamma intersection with the u square. So this will be a contradiction, almost. So this, you see, we have B1 with some ball, and inside we have many points, gamma 1, gamma 2, up to gamma m plus 1. And if I take the u neighborhood of all of them, there will be disjoint. This will gamma 2u, gamma 1u, gamma mu. There will be disjoint. But it cannot be, because we defined m to be the volume of B1 divided by the volume of u. So it's a contradiction. But it's not I made a mistake. You see this, when I multiply one of them by u, maybe I'm going out of this. So what I should have taken in the beginning is not the Haar measure of B1, but the Haar measure of B1 times u. And then it's okay. Okay, so there was some typo in the beginning. When we defined M, we needed u here. And then it's a proof. So that's a proof of the Margulis lemma. Maybe let me spend 1 minute just to explain this. Why if two elements, how do you know that the displacement is less than? So this is a general fact. So if d alpha x is less than well, let's say this is the following lemma behind this. Lemma, we'll finish in 3 minutes. You need this place?
Yeah, it's booked from
Okay, 3 minutes. So lemma, maybe we will. So lemma, if so the displacement of alpha beta x is less than the displacement of plus the displacement of beta x. And why is that? Because the displacement of alpha beta x is, I multiply by the inverse, everything is by isometries. And this by the triangle inequality less than beta x. X plus dx alpha inverse x